This next slide is about how to think about looking at and interpreting data that's on graphs. So I'm going to talk to you about the things that you want to think about when you're looking at a graph, and importantly, what it means when we look at horizontal and vertical lines. So the first thing you need to be looking at when you're looking at a plot or a graph is what are the axes, and if there's a plot that doesn't have axes labels, that's a problem. So the first thing that we're going to want to be doing is looking at our axes. So read our axes. On our y-axis, that is going to be our dependent variable. What we're really saying in this problem is that pH is dependent on our x variable, which is our independent variable. So what this plot is showing us is how the pH will change as the percent dissociation. So I'm going to highlight here on this plot, it kind of shows us down here that it says that the x-axis, is H plus ions dissociated per molecule. So here's a couple of reasons I don't like that title. It seems to imply that you can have 0.4 protons dissociated per molecule. Well, proton dissociation is a binary event. Either the proton is with the molecule or it's deprotonated and that proton belongs to the solution. So really, protonation state on an individual level is 0 or 100%, but on a population level, we can have sort of these gradations. So I'm really going to be referring to this as protonation state as a percent dissociation. And again, it's of our population. So this is a percent dissociation. And this is on a population level. Okay, so when we're looking at things on the x-axis, it's telling us what percent, again here is a fraction, of our population is dissociated. So as our percent dissociation increases, more of our population has given up our protons to solution, we're going to see a change in pH. Okay, so we need to be looking at our axes to make sure that makes sense. And the second piece is oftentimes we're going to be looking at plots and we're going to be asking the question, what happens if I have a horizontal line or a vertical line? So the key to this is understanding that horizontal and vertical lines really allow us to hold one variable constant. So we're going to be talking about drawing horizontal and vertical lines. Okay, and so that is going to be holding one variable constant, either our y variable, our dependent variable, or our independent variable, which is our x variable. Okay, so I'm going to walk through this plot and I'm going to talk about what we're really seeing with a horizontal line first and then a vertical line. And it relates to concepts that we've been talking about in class, which ask us to think about pH, protonation state, pKa values, and so forth. So let's first talk about our horizontal line. Okay, so I'm going to draw a horizontal line right about here. So there's my horizontal line. So I'm going to be calling or labeling anything with my horizontal lines. I'm going to be putting that text in red here. Okay, so what we are doing when we have a horizontal line is we are holding pH constant, because pH is our y-axis variable. It's our a dependent variable. So we're going to be holding pH constant. And in this case, it's going to be around 6.8 because of where I've drawn my line. So when we're holding pH constant at 6.8, here's the question we're asking. What is the protonation state at this pH? So for each of these horizontal and vertical lines, we're going to be talking about, well, what question are we answering or addressing when we hold one of those variables constant? So what is my protonation state? at this pH. So how you determine that is you basically travel across your horizontal line until you intersect your given plot. Okay, so let's take each of these independently. Let's talk first about NH4+. You're going to see here that we've got 3 different species. We've got NH4+, wrote over that there, but that's H2PO4-, and then CH3COOH. So let's start with the NH4+, and when I drew this red horizontal line, I intersected with my blue line for NH4+ very early on in my X species, essentially equating to about 0. So what this says is, what is the protonation state of NH4+ when I am at pH 6.8? It's about 0%. Let's take our next guy, H2PO4-, and when I take my line across here and I stop where it intersects my line, I'm going to be at about 50% deprotonated. Okay, and let's do our last guy here. When I've got CH3COOH, let's do our same thing. I'm going to be, again, taking this red line and finding out where it intersects with my green line. It intersects at about 100%. Okay, so one of the things that we're going to see here is there are some special things that happen when we have halfway values. So I'm going to box this guy right here, and we're going to come back to that one. So that's the question we're going to answer when we have a horizontal line. What's the percent dissociation, or really what's the protonation state at a certain pH? Okay, so the protonation state for NH4+ is essentially fully protonated because the percent dissociation is 0. It's a 50-50 mix for H2PO4-, and then it's 100% deprotonated when we have CH3COOH. Okay, and maybe your wheels are already turning with what this means, but let's go ahead and do the other side first. Let's do our vertical line. Okay, so our vertical line. Okay, and I'm actually going to use the vertical line that they have here. I'm going to color it blue so we can see what I'm referring to. And again, anything that I'm going to be talking about with these vertical lines, I'm going to highlight with blue here. Okay, so when we think about vertical lines, we need to think about, well, what am I holding constant for that vertical line? So in this case, what I'm holding constant is I'm going to hold my percent dissociation constant. Okay, I'm holding my X value constant, and in this case I'm holding it constant at 50%, because that's where I've drawn my line. Now you could draw these lines, these horizontal and vertical lines, wherever you want. I've chosen to kind of go at some specific points here to highlight a few points that we're going to talk about with acids and bases here. Okay, so the question that we're asking when we draw this vertical line is, what is the pH that's required for 50% deprotonation? So that's the question, is what is the pH required for 50% deprotonation? Now I will say I'm sort of interchanging these terms, deprotonation and dissociation. So they're referring to the same thing, right? Because deprotonation is the dissociation of a proton from our acid here. So what is the pH required for 50% deprotonation? And just like we did with our pieces before, and I'm going to go through NH4+, H2PO4-, and then CH3COOH, I'm going to ask the question, when I'm drawing this vertical line, where do I intersect my plots? And then I'm going to go over to my y-axis and ask what that number is. So let's go ahead and do that for these 3 guys. So for NH4+, if I want to be at 50% deprotonated, or 50% of my acid has dissociated, I need to be at pH 9.3. H2PO4-, my pH is going to need to be 6.8. And then for CH3COOH, I need to be at 4.76. And so if you don't see those numbers here, right, come down here. Where do I intersect my line? Go over 9.3. Where do I intersect my line here? Go over 6.8. Where do I intersect my line? 4.76. So there's something special here with these species that I'm outlining in green here. So, and there's something special at a halfway value of when I am 50% deprotonated. So when I ask the question, what is the pH required for 50% deprotonation? Well, that's sort of the definition that we gave for a pKa value. A pKa value is the pH you need to be at for your molecule to be half deprotonated, or your acid to be half dissociated. So these halfway values are really important biochemically. So these halfway values are really important. And here, the halfway value is pKa. And remember, we defined pKa as the pH where half of your population of molecules is deprotonated. And note that this is consistent with some values that I already told you needed to know. pKa values for protonated amines are between 9 and 10. Well, that's what ammonium ion is. It's a protonated amine. pKa values for carboxylic acids, okay, are between 3 and 5. And that's what we see here for acetic acid, okay? So, and when we are at the pKa value for H2PO4-, the singly deprotonated form of phosphoric acid, okay, here we have our pH is equal to our pKa. So I hope that gives you a good understanding of how to look at graphs, how to think about holding X and Y values constant so that we can make interpretations about what graphs are showing us.